Hello everyone, welcome to today's session. We have Massamichi talking about baby universe corrections to the time slices of two-sided black holes.
Thanks for introduction. So it is my great pleasure to be in India for the first time, and it's pretty much enjoying here, and the weather is great compared to Kyoto, actually. And today I'll be talking about hopefully work coming up soon, based on these two papers with Shamin and Shono and Kazuyoshi. And so this talk is basically about what's the time size in two-sided black hole and jet tidal from gravity, and the Euclidean one-fold correction to that. So let me begin by the very basic thing. So we know that the black hole entropy is given by Bekenstein-Hawking entropy, which is the area of the event horizon divided by 4G Newton. The most important thing is that this black hole entropy is finite, even though it is a pretty large quantity. The immediate consequence of this finiteness of black hole entropy is that the spectrum of the black hole must be finite, and therefore the spectrum is also the discrete. So that is the consequence of this Bekenstein-Hawking entropy. And the question, the important question from this discreteness is that how do we get the continuous, this discrete spectrum from the continuous spacetime in a gravitational passing theorem? So this continuous the spacetime is closely this is the origin of the famous paradox such as the black hole information paradox or the related paradox called the black hole problem. And we learned recently that this discrete spectrum can be captured by the so-called introduction of the Euclidean one-folds. So in the recent the series of papers in 2019, that once we include the Euclidean one-fold contribution into your replica manifold passing integral, then you can get the correct unitary entropy for the Hawking radiation, so reproducing the so-called page curve. The reason why we have a very simple description of this derivation page curve is that this, without knowing the UV details of the quantum gravity, is that because this Euclidean one-folds correspond to the ensemble averaging over the microscopic quantum gravity theories. So we could say more about this, what are really captured by the Euclidean one-folds. So if you consider, so let's consider a black hole and do a quantum state, and suppose we have the particle with flavor alpha inside the black hole interior. Then the EFT says that if the alpha and beta are different, then they should be orthogonal. So the overlap should be given by the Kronecker delta. So that's the consequence of EFT. But in the quantum gravity, this is no longer true. And you have a subreading correction, which is exponentially suppressed, while it is a finite fluctuating van der matrix element. Yes? Yes, yes, yes. Yeah, so if you take the ensemble averaging of this right-hand side, then this second term is not only exponential suppressed, but also the second term averages to 0, so it is not visible. But what Euclidean one-fold will do is that the Euclidean one-fold capture this statistics of the second random matrix element. And that is why the page count was captured by the replica one-folds. So in the following, I will consider, instead of the particle with flavor, I will consider the bulk state defined by some geometric quantity. So more specifically, I will mainly discuss in the JT gravity, and I will consider geodesic time slice, with the fixed geodesic length. So I will mainly consider this type of configuration. And I will consider the dual state to this fixed length time slice. And consider the same, this orthogonality property. So in the leading level, without any handle corrections, when the two lengths are different, then these two states must be orthogonal. But now you encounter the serious question. Because we have the finite black hole entropy, so the number of quantum states in a Hilbert space is finite. But now we have the continuous family of state, which are orthogonal to each other. So it seems, even though, it seems like this length state gives you the too much state in your Hilbert space. And at least it should give some over-complete basis to our Hilbert space, which is finite dimensional. So this is the puzzle at the first sight. So to say again, so we have an infinite number of states, which is labeled by continuous number L, and this is in contradiction with the finite dimensionality of a Hilbert space. And again, so this question, this puzzle can be addressed by considering the Euclidean one-folds. So even when the lengths of the geodesic are different, we no longer have an orthogonality, but we have a finite non-zero term due to the Euclidean one-fold that connect the two half-disk geometries. So due to this non-orthogonality, we can, it is still consistent to have a finite dimensional Hilbert space with this infinite number of the length, the fixed length state. But the consequence of this non-orthogonality is kind of serious, or very problematic. Because once you have this non-orthogonality, then the meaning of the length is very ambiguous. For example, you can't construct the Hermitian operator which satisfies this eigen with eigenstate decomposition, because you can just consider the ket with L prime with different L. So, yeah.
Sorry, I might be sort of saying something you'll come to, but Your picture, doesn't it suggest that instead of going to the one boundary system, we should go to the multi-boundary case once you include wormholes? Because if I were to try and cut your diagram, you would have L and also a kind of length of that wormhole.
You mean the baby universe sector?
Yeah, so maybe this is going to be something to talk about. But in that wide, bigger multiverse kind of system, maybe you have well-defined operators corresponding to different lengths.
All right, so actually, so the Hilbert space I'm considering now currently is, so I'm embedding this length state into the boundary Hilbert space. So boundary CFT state, but zero plus one dimensional system.
I have a small comment, if that's okay.
Yeah.
So apart from this, there are also other contributions where there is a finite volume of space-time between L and L prime, okay, which are also like non-perturbative, like other types of non-perturbative corrections to the inner product. There could be some handle body stuff in between, and that will actually make even without you introducing extra baby universes, will create non-orthogonality between different L states.
So the more precisely, I'm considering the passing integral with a boundary condition is this A-disk boundary, geodesic boundary, and A-disk boundary, and do all the space-time geometry which fulfills this boundary condition, which included this type of geometry. And due to this non-orthogonality, we can't talk about the probability distribution proportional to the kind of projection, mimicking projection by the length.
This is not automatic, right? So for example, in coherent states, it's an overcomplete basis, but there's a very similar decomposition of identity you can write down. So will you prove that this is not possible, or is it obvious in some way? Or?
So I'm just saying that since L is not orthogonal, it doesn't give you a projection at least.
But the same thing happens with coherent states. The xp and x prime p prime are not orthogonal, but still you can write down a resolution of identity in the coherent state basis.
Right. Yeah. So I'm going to construct the projection using this length state, but it's not very coherent state. So it's yeah, you will see. Yeah, what I will do. So this is the aim of this talk. So I will construct a fixed length black hole white hole orthonormal basis. So orthonormal is the important part of this, and which incorporate the effect of Euclidean wormholes. So first of all, I was talking about the fixed length state, but it's not really suited to talk about time evolution of TFD state in gravity, because it is a mixture of the like expanding TFD state and the contracting TFD state. So expanding part is often called the black hole, and the contracting part is often called the white hole. So because these two lengths are the same. So I will construct this type of black hole and white hole basis, and using these orthonormal basis, I will define the probability of having the certain length, as well as the transition probability about Sumfield double state into the white hole, the contracting two-sided black hole. So from now on, I will primarily talking about the Sumfield double state in JT gravity, and decomposition in terms of this newly defined orthogonal basis, orthogonal black hole white hole basis. So is there anything to clarify? Any questions? Yeah.
Fully sure. I thought these were states which existed in, say, suppose I were to try and quantize the bulk theory,
Right.
subject to boundary conditions, then these would be states in that bulk description.
Right.
But are you thinking of it like that, or are there states in the boundary CFT?
Also, okay. I will, maybe it's easier to look at the form of the state. So yeah, I'll use it in this moment. Right. So yeah, this is just a review slide for JT gravity. So JT gravity is 1 + 1 dimensional diatom gravity due to matrix integral, and it has a infinite number of the handles geometries, and it's due to the matrix integral. So basically, this ensemble averaging over the 0 + 1 dimensional systems. And one important point is that because this is the second term, due to the, once you integrate the diatom, you get the constraint that R equals -2 being the hyperbolic geometry. So I will consider this JT gravity, and I will consider the following the so-called geodesic length state defined by in the following way. So let us take a closer look at this state. So this state is some superposition of the energy eigenstate of a microscopic Hamiltonian at the boundary. And I'm considering the microcanonical ensemble. And the coefficient.
Can I ask a question?
Yes.
Is there any specific reason to choose two states? One is in white hole, another in black hole. I thought, can we also prepare like gate from the black hole part and, for example, bra from the white hole part?
Okay. So this, yeah. So this fixed length wave function has can be decomposed into the black hole part and white hole part, which is basically the expanding part in the time evolution and the contracting part in the time evolution.
Thank you.
And this wave function is the same wave function in the JT gravity with the disk topology with fixed geodesic length and the ADS boundary without no handles at all. So this state is designed to reproduce when you take the overlap with the energy eigenstate, then you get this disk wave function. So this is the definition of the length state. So because I'm considering the microcanonical ensemble, the number of the state is finite. So I'm considering the finite dimensional Hilbert space. So as I said, we decompose the fixed length state into black hole state, contracting state and expanding state, and which are defined by this expressions.
Sorry?
Yes?
The right-hand side of those two equations don't have L anywhere.
Sorry?
The right-hand side doesn't have L anywhere.
Oh, sorry, this is, yeah, this part should be, let's see. So I think I missed something here. Let me say that, so we can decompose, so at the large L limit, sorry, I think I have a typo here, but so if we take the large energy limit, it can be written like a, right, yeah, it's basically like e to the is. And in the time evolution, so this part corresponds to black hole, and this part corresponds to white hole.
An exact decomposition.
So if you use a Fourier transform, like the second, so I have typo here, but you can decompose into this black hole contract part.
I see. This is like, for example, this is like fixing both, like in one particle quantum mechanics, it's kind of like fixing both x and the sign of x dot. Right? And you're saying that something
no,
like
so,
does that job.
So it's basically you are considering the fixed length state and decomposing it into, yeah, so no, it's not really the, let's see. So I'm decomposing fixed length state and constructing a projection into the white hole state and a black hole subspace. And these the black hole state and white hole state are just a consequence of that projection.
Okay.
In classical, near classical physics, wave packet which have two components, positive momentum and negative momentum for the center of your wave packets. And then you write psi of x. There will be a e to the minus I average p dot x plus I.
Yeah.
It's like that.
Yeah.
That makes sense. I'm just confused about this, the exact projections that here, because is this an approximation or are there really two subspaces where, so the way I think about it, black hole and white hole differ by the sign of L dot. That is it, right? So like, are there really two subspaces with different signs of L dot? Or is this some approximation? If you gave me the WKB form, I would be completely happy with that. It's an approximate decomposition. But this looks a little more exact, so I'm a bit, I'm asking about that.
Yeah, I think at this point it's the decomposition exact, but after the decomposition, whether I have a fixed length or not is not very clear. Yeah, so it's not maybe not.
I see. So your L is not fixed anymore. It's
right,
T
yeah,
and L. Okay, that makes a lot more sense. Thank you. Should we be worried at this point about non-perturbative gauge transformations relating these two, or?
So at this point, I'm only considering at the disk level. So I will consider the correction to it from baby universes. So from now on, I will use this classical relation between the time and the classical length. So which is dictated by the classical geometry. So we can consider the inner products of this black hole state and white hole states, and it can be given by in the following way. So in order to have the orthogonality, the condition is to have a TL being the quantized. And as a consequence, the consequence is that in order to match with the dimensionality of the Hilbert space, the TL can run from minus TH over 2 to TH over 2, where the TH is the Heisenberg time. So let's first start with this TL state without considering the baby reverse corrections, and take the projection of Tanghu double state into the fixed TL state. The result is as follows. So suppose so this is a plot for this the overlap. So as we expect, so at the classical value, there's a delta function peak correspond to the classical geometry. And once we incorporate the baby universe effect, we get a new contribution, this second term, which is given by the following expression. So this stays constant for most of the TL, but it has some linear dump around the classical value.
Sorry, Euclidean wormhole contribution is the baby universe contribution, or it is different?
Sorry, yeah. So this second term is from the baby universe correction.
Oh, so is it same as Euclidean wormhole contribution or different?
Yes, it's Euclidean wormhole correction.
Okay, thank you.
I didn't understand. What calculation do you do in GT gravity to get the second term?
All right. So what we do is that let's see. So we have the TL state, and it's given in terms of the energy eigenstate. And we have a TFT set here. So it's energy E1 and energy E2 inside. And you do you have the density state 2-point function times some functional and the integration. Yes. TL is the yeah. Sorry, this is content part typo. Sorry. So yes.
Can you remind me whether this TH appeared?
So yeah, TH is defined by this Heisenberg time. So it's e to the s times the density of states. So density state, normalized density of state. So basically, this part is the e to the SE. SE is the black hole entropy at micro canonical black hole entropy times some constant 2 pi.
Okay.
So it's a pretty large quantity. It's a time scale. It's correspond to the inverse of the mean level separation.
And why does this quantitative change appears around this TH in the probability distribution?
So here I'm using the okay. So at this time, so that the significance of this time scale is that it starts to see the discreteness of the spectrum. So because it's a time scale inverse to this reverse separation, and at that time, so it's similar to the spectrum form factor, where you have a rampant plateau. And here is some kind of, due to similar mechanism, we have this constant growth and plateau.
Why does this discreteness spectrum leads to this constant state overlap?
So one intuitive way to say this, actually this result will be corrected in later part. But actually, so I could say something. So actually, the constant in a product is kind of problematic, because if you think you can consider infinitely large TL, so if you consider integration over TL and consider the expectation value of the length or something, then it's necessarily divergent.
Thank you.
But one intuitive way to think about this is that after very late time, your wave function, your TFD state spread over whole length state. So the black hole, white hole state are equally probable. That is one way to say. So in that case, it's no way to distinguish between states. So we have the issue have the divergent probability to find a black hole state. So here's the main idea to reconcile this problem. First of all, we should, as we said earlier, we should restrict the range of TL to be finite, controlled by the Heisenberg time. Then we have the correct number of state matching with the microcanonical dimension of the microcanonical Hilbert space. But at this point, these states are not orthogonal yet. So still we have a problem that the overlap is not really the probability at this point. The main idea is to consider the projecting out a shorter length state from the black hole states. That's the main idea.
And this is a continuous basis still, right?
This is not continuous due to the constraint here, due to microcanonical ensemble array constraint. It's a discrete.
So, but in a particular, why doesn't the randomness of the spectrum turn up here?
Okay, so in this computation, I'm already using the randomness. So this quantity contains the density of state 2-point function. So I'm using the sine kernel approximation at late time. And that's where
Yeah, sorry, maybe I asked the question the wrong way. So normally I would think that the discrete basis for the microcanonical ensemble that's relevant is the sort of UV basis of energy eigenstates, which would be like, and the spacings between these guys would be completely random, right? So is this discrete basis supposed to somehow correspond to this UV basis, or is it like just something you made up that does the job?
So you mean these discrete states? So they are just they just correspond to the black hole white hole state after decomposition, and it is pretty random with the so if you expand in terms of the energy eigenstate, then it has a okay. So in a sense, that randomness is contained in here. So the main Mm-hmm. Mm-hmm. Oh, okay, so that's first term? So the first term, if you have a sufficient large delta E, then it becomes almost like a delta function. Mm-hmm, mm-hmm. Okay, so actually, so this delta E prime, so maybe I'm not understanding your question, but this delta E prime is not relevant here. Is that your? Mm-hmm.
Confused about why the inner product is as large as that. Why doesn't it go to zero faster with as a function of ti minus t? In fact, it's related to a random phases question that Ronak had. Let's say you have these random phases, so you have this discrete basis, and if you take ti minus t to be well separated, then you get a lot of random phases adding, but the number of random phases is e to the s, because they're e to the s states. So the inner product you expect to be e to the minus s by 2, because you have so many random states adding. But this doesn't seem to have an exponential of that kind, but maybe I'm missing something basic.
Yeah, okay, so yeah, let's see. So this is not really delta function because I'm taking delta E to be small in the order one sense.
But still large to contain a large number of eigenstates, right?
All right, yeah, okay, that's true. And I'm in this plot, I'm just writing in terms of in the scale of th, Heisenberg time. So it still has some. If you zoom in, then you have still some kind of small overlap is different. It's not really concentrated at the. Okay, as you said, it contains some other eigenstates. That's true. Yes.
You're offline, yeah.
Yeah, thanks for the question. So the main idea is to project out the shorter length state, and using that, we can construct the orthogonal, the black hole white hole states. And the construction of such projector, we know we learned from the recent study, can be done by considering the replica trick. So I'll consider this p hat TL, which is designed to project into the state, which has a length smaller than L. So you can take the n to the positive real number and take the n goes to the 1 limit. And using this projector, I will consider the state, which is projecting out this shorter 1-4 states from the original black hole states. So if we construct this set of states, then it is they are manifestly orthogonal, and that can give a well-defined probability distribution. So that's the main idea. And the rest of the talk will be rest of the 3 slides will be how to do the computation. So we will be in order to compute the length probability distribution, it is very convenient to consider TFD state, the expectation value of this projection on the TFT state. So this gives you a probability that your TFT state has a state whose length is smaller than L. And using replica trick, we can express in terms of the density of state correlation function, n+1 point correlation function times these y functions, where this functional is defined by the projection. Okay, so this operator with an energy eigenstate. So this is the definition of y. And by just taking the difference by derivative by TL, then you can get the length distribution, probability distribution. Yes.
So I didn't understand the need for the replica trick in constructing the projector. You just had, what is, and second of all, why is it n going to 0 and not n going to 1? I don't understand.
Okay, so the point is that if you use, the point is that because this length, the TL state are not orthogonal to each other, and it doesn't, so if you consider the non-zero eigenvalue of that, of this operator, its eigenvalue is not 1 due to this non-orthogonality. So I wanted to queue that part, and to do that, it is convenient to consider the replica trick. Yes.
Is it okay with the uncertainty relation? I was wondering, so you start from microcanonical window in terms of energy, and now you are projecting to the really shorter length scale. And I was a bit concerned about, like, since the energy and length are like in the conjugate variable to each other, so there might be uncertainty relation that which prohibits to focus on really shorter length scale.
So yeah, so certainly this TFT state doesn't have a fixed. It's not the eigenstate of a length operator, if I could define, and so basically, so here I'm considering the so here by using this the projector, I'm defining the length operator, and defining the length operator is fine. It's just the uncertainty relation is about about state. So, but and this state is not the eigenstate of the length. So it's not.
Okay. I ask later.
So first, let's consider first by the classical contribution. So in the classical regime, the density of state n+1 point function is given by the product of 1 point functions. And in that case, we can find that this QTTL is given by the Heaviside state function. So it is very consistent with the classical interpretation that up to TL, there's no state. Okay, so this is consistent with the classical expectation that the wave function is concentrated at the classical value. So if you take TL bigger than TL, it becomes 1. And the more interesting contribution is coming from when we have a more non-trivial contribution from density of set correlator. So here I'm only considering the two-point function is connected. And so there are many other bilocal contraction, but I'm just only taking the two of them to be connected. So even this assumption is a bit crude, but we find a very interesting result. So this is the main result, and first two terms is just obtained by the integrating this thing, which we have computed earlier, like this. And this is a kind of probability distribution, ignoring the orthogonality of the black hole states. And this second term is the correction from non-orthogonality. And this is the plot of this function Q. So this is for the array time when t is smaller than the half of the Heisenberg time. So we see that Q grows linearly in time, and at the classical value, it turns into 1. And intermediate range, we have the linear T growth, but at this point, even though we should have a probability 1 at the end of this plot, we don't have it. So we need a higher order correction to look at this time window.
Is Q a probability distribution or some sort of cumulative probability, like integral from TL from 0 to?
Right, yes, integral of P.
Yeah, it's a cumulative thing, okay.
Yeah. So it should be 1 at the end of the. But somehow at the late time, when T is greater than the Heisenberg time, it has a linear growth, and it gives the correct probability at the end of the. But it's outside of the range of approximation, and it's not obvious whether this is correct answer. But it is at this point it's still consistent.
A while back you said TL states don't have fixed length.
Say again?
A while back you said TL states do not have fixed length.
Mm-hmm.
But now you're interpreting probability of TL as a length.
That's right.
Length.
Yeah.
Like,
that's right.
What's going on here? Is this interpretation corrected at subleading orders, or is it just is the interpretation corrected at subleading orders?
Yeah. So right. So okay. Let's see. Yeah. Okay. So at this point. Yeah, I think it's an interpretation at this point, yeah.
Exact result, or like, do you assume any specific replica symmetry configuration when you analytically continue n goes to 0?
So here I'm only considering this 2-point function. I mean, only two density states are connected.
Mm-hmm.
And I'm not assuming anything other than that.
Is there any reason that you can focus on this two product 2 terms only?
So this should correspond to the time is sufficient small compared to the Heisenberg time.
I see. Thank you.
So we have seen that the constant probability density for the shorter length state, and we have the zero probability for the longer length state, as we can see from the this probability being 1. So we can generalize it to the black hole white hole probability distribution, and by considering the more generalized projector and taking derivative of this projector, we can get the probability distribution to get the black hole state. And these black hole white hole states are manifest orthogonal, and by definition, we have this property. And using this definition, we can get the following expression. And indeed, for the early time, we can get this quadratic increase of the white hole probability distribution, which is matches with the Stanford-Young paper up to order 1 factor. So if even though this might be, this late time regime is out of the validity of our approximation, we find that at a very late time, the probability of finding black hole and the white hole are the same, and given by the 1/2. So it corresponds to the Susskind grade 4. So having at late time TFD state is a equal mixture of the black hole and white hole. So I just
asymmetry of black hole and the white hole appears. What is the origin of this asymmetry in the early time and symmetry in the late time?
So at the early time, there's only a black hole state. It's the classical geometry peaked at the black hole geometry. And at late time, we have so this is the white hole probability, which is quadratic in time. And it grows at late time, and at some point it's coincide.
Is it apparent from the wave function?
It is not apparent at all. So it's basically what's happening is the TFD state spread all over the black hole and white hole state equally. So there's no distinction between them. Yeah, so it's time wrapping up. So just so we can compare with the other differential length operators, and it seems like it's in both cases it is not trivial to see them whether they are coincide or not. But please ask me after the talk. And so we have some interesting ambiguity in the constructing a black hole, the white hole basis, because we can pick up the origin of this TL state at any point. So if we, for example, so we have been taking T0 to be 0, but we could in principle take T0 to be TH. And once you do that, then the various probability we are considering looks very different from the T0 equals 0 case. But we have to note that so as we increase the TL away from T0, because the baby universe correction, this TL state is TL Tudor state, which is a consequence of projection, is very different from TL state. So the kind of geometric interpretation is only good only when the t0 is close to t0. So there's no, it is not immediately the contradiction. So this is some schematic figure. So there's future directions, and yeah, I should stop. Okay. Thanks for the question.
Questions?
Hi. Hello. Can you say something about the last point you wrote there about the Würzburg corrected? No, in the last slide.
Last slide?
The universe corrected Würzburg action.
So we are considering the the Würzburg action in the presence of Euclidean wormhole. So in the similar to the length, with the saturate will be get the large correction from baby universe at Heisenberg time. We can talk about doing the gravitational passing integral for the Würzburg action as well. And in that case, we also it also received a large correction from baby universe.
Isn't this Wheeler-Dewitt action Lorentzian thing? Like, how would you include?
To compute, we use the analytic continuation from Euclidean to Lorentzian. And yeah, okay, so it's the Wheeler-Dewitt patch is defined by fixed extrinsic curvature slice, and we consider the Euclidean fixed extrinsic curvature slice and analytic continue this extrinsic curvature to Lorentzian signature. So there are two analytical continuation. One is the analytic continuation in time, and also the analytic continuation in the extrinsic curvature.
So this thing you pointed out at the end with like choice of T naught, is that so if I'm interested in like psi TFD at 0, can I expand it in TL for T naught minus TH to T naught plus TH for any?
You mean the kind of disconnected?
Yeah, like I'm wondering if the choice of T naught is in the state of the TFD state or in the basis.
Okay, so the T naught is coming from. It has nothing to do with the TFD state. It's coming from the orthogonality between the TL states.
Massamichi again.